Can you hear me?
وعليكم السلام.
حياكم الله. وعليكم السلام. Okay, I hope that you're almost ready for the exam, inshallah, tomorrow. I'll mention something because yesterday, if you remember, one of you suggested if I can give a problem session. Well, Hagiga, I'm really sorry, I'm not going to be able to give a problem session. But and the reason is, starting yesterday, things really got clobbered on me. I have so many things that I have to work on at home. The water pump basically broke, let's say, think of it this way. Okay, so I have to work on it. I'm not going to say we don't have water, but we have very little water. In addition to, even your exam, I worked on it yesterday, I couldn't finish it. So even your exam is not done, okay? But I will be available, inshallah, after the class for maybe 2 hours or so if you want, from, let's say, 1 until 3, even if I have to until 4, I'll be happy to if I find that a lot of you have questions and I need to stay until 4, it's okay, right? But yeah, I'll give you an extended office hour today, right? Starting from 1 until I find that there's no one who has any additional questions who want to ask, then I'll leave, okay? So my apologies for this. Honestly, I would love to give you a problem session. Maybe you can do it before the final exam, but today is going to be very difficult for me, okay? Especially as I mentioned that I have to go home, work on the pump, and hopefully I can finish it maybe in 2 hours or so, and then try to finish your exam. I wrote most of the exam, but not all of it. There are maybe a couple of things that I need to modify here and so on, and I need to solve it, make sure that it can be solved in a reasonable amount of time, and it's reasonable. It's not too difficult, it's not too easy. Okay, so my apologies for this. In fact, yesterday I talked with 2 or 3 of you for maybe an hour and a half or so. So I'm willing to do it again today if you want. Okay, so let's go to the lecture notes. And if you remember last class, at the end, I think last maybe 20 minutes or so of the class, we talked about the concept of the Fourier transform, Fourier transform or Fourier transform. Okay? And we said that the Fourier transform is just, it is related to the Fourier series. However, the Fourier series works only on periodic signals. The Fourier transform is designed for non-periodic signals, but you can also find the Fourier transform for periodic signals. I mean, the Fourier transform does not say if you put into me a periodic signal, I'm not gonna find its Fourier transform. It's just that sometimes some of the periodic signals do not have a Fourier transform. Yeah, there are some let's say special situations in which periodic signals do not have Fourier transform. But the important point, and this is what, if you wanted to summarize, let me say it this way. Fourier series, mostly for periodic signals. Fourier transform, mostly for non-periodic signals, okay? However, some periodic signals you can also find their Fourier transform. And I showed you last time, although kind of quickly, I hope that you understood what I said last class, but basically this is the Fourier transform. This basically is the Fourier transform of a signal x of t, where x of t here may be periodic or it may not be periodic. How do you find the Fourier transform? You take that x of t multiplied by e to the power of minus j omega t, not omega 0. There's no omega 0 here because we don't have a periodic signal. Even if we have a periodic signal, we don't plug in omega 0 there. It's omega. It's a variable. Omega there is a variable. Like k in here was like a variable. K is equal to 0, 1, 2, 3, 4, and so on, depending on what value we want. Also, omega in here is a variable that we can evaluate the Fourier transform at any value for that variable, any value of that variable. Okay, so it's minus j omega t, and then you integrate with respect to t. Okay? So this is basically called the Fourier transform, and we usually give it a name, which is capital X of omega. Meaning, if I'm taking the Fourier transform of small x of t, the result becomes capital. If I'm taking the Fourier transform of y of t, okay, let me just reduce the font size in here. Okay. If I take the Fourier transform of y of t, t. Then the result becomes capital Y of omega. Okay? So we know that we're talking about the Fourier transform because we're talking about a capital letter, and the argument there is omega. Okay, Juan? So capital X of omega is nothing but the Fourier transform of small x of t. Now, what is the meaning of capital X of omega? It is called the spectrum. It is the Fourier transform provides us with the spectrum of the function or the signal x of t. The spectrum basically, and from its argument or its, let's say, variable omega, it's basically a plot of the content of that signal x of t, but not versus time, like what small x of t gives. Small x of t gives us what is the content of that signal versus time. At specific time, this is the value of the signal. This is the voltage, let's say, of the signal at t equal to 3. T equal to 3 seconds. This is the voltage of that signal at t equal to 2 seconds. This is the voltage of the signal at t equal to 5 seconds, and so on. This is basically what x of t gives us. That x of t, it gives us the value of the signal at different time instance. A capital X of omega gives us almost the same, but it gives us the voltage of that signal versus frequency, not versus time. So it will tell us that at that frequency, I have 3 volts, something like this. At that, at that frequency, for example, 7 hertz or 7 radians per second, I have 2 volts. At that frequency, I have 9 volts, and so on. So this gives us what is the spread of the signal, not versus time, but versus frequency. And this is why we call it the spectrum. Spectrum, طيف. In Arabic, it's called the طيف. What is the طيف? It's, for example, we know that the rainbow, they usually call it طيف. Okay? I don't know what they call it. It's basically the spectrum of white light. And if you take white light and put it into anything that will split the white light into its specific frequencies, you get the spectrum. This is why white light, the spectrum, let's say, of white light is all colors, starting from red to yellow to orange and so on, all the way to violet. The rainbow is called the spectrum because it is splitting the signal, x of t or whatever, into its different frequencies. Not versus time, but different frequencies. Okay, Juan? Right. Talk about the Fourier transform. When we talk about the Fourier transform, when we talk about this, the Fourier transform takes a signal from time domain and transforms it into what we call frequency domain, x of omega, capital X of omega. Now, if we take a signal from time domain and move it to frequency domain, someone may say, does it mean that we can take a signal from frequency domain and move it back to time domain? And the answer is yes. One of those is called the Fourier transform. The Fourier transform always takes the signal from time domain and shifts it to frequency, moves it to frequency. The inverse Fourier transform, or what I'll abbreviate as IFT, the Fourier transform, I'll always abbreviate it from now on FT. Instead of each time writing Fourier transform, I'll write it now as FT. The inverse Fourier transform is abbreviated as IFT. It takes a signal from frequency domain, which means it takes x of omega and transforms it back to x of t. So to go from x of t to capital X of omega, this I have to do the operation which is called Fourier transform, which is basically this operation that I have there. The integration of x of t multiplied by e to the power of minus j omega t, integrated with respect to t. To go from x of omega to x of t, I have to do the inverse Fourier transform, okay? Which will take for me capital X of omega and shift it back to, or move it to, change it to x of t. Now you see that both the Fourier transform and the inverse Fourier transform have almost the same shape with minor modifications. They have almost the same configuration or the same, let's say, structure. Yeah? Forget about this for the time being. Forget about this. A minute. I have an on top. If I have x of t multiplied by e to the power of minus j omega t, with respect, integrate with respect to t, you will move this to capital X of omega. Now, if you have X of omega, and you want to shift it back to X of t, integrate it from minus infinity to infinity, which is exactly the same. But don't multiply it with e to the power of minus j omega t. Multiply it with the kind of the positive, e to the power of positive j omega t. Okay? It's the, in fact, it's the complex conjugate of this. The complex conjugate of e to the power of minus j omega t is e to the power of positive j omega t. Right? So multiplied by e to the power of j omega t. And do not integrate with respect to t, but clearly this, you see, this is a function of omega. It's not a function of time. So multiply it by something that contains omega in there, and integrate with respect to omega. And the last modification is you have to divide by a constant, which is 1 over 2 pi, and divide by 2 pi. And this will transform for you the signal from frequency domain back to time domain. Clearly, when I multiply anything by something that contains omega and t, and I integrate with respect to t, t disappears and omega remains. You think of it this way. This has t. This has, let me just erase the stuff that I have there so that I don't confuse you. Look in here, gentlemen. This thing here, the yellow thing in here, okay, and the orange and the red, okay. Clear? The yellow is a function of time. Yeah. The orange contains both time and frequency and omega. Clear? And I'm integrating with respect to t. Okay? So what happens? You have something that's a function of time, multiplying it by something that is both a function of time and omega, and integrating with respect to time, t will disappear, and what will remain is omega. And this is why the output is always in terms of omega. It's not if you see someone telling you that the Fourier transform or the spectrum of a signal, the Fourier transform of a signal is x of t, capital X of t, something is wrong there. The output of the Fourier transform has always to be a function of omega, not a function of time. Now, if you go to the opposite one, this is a function of omega, this is a function of t and omega. And we're integrating with respect to omega. So clearly, the product of those two will be a function of t and omega. When you integrate with respect to omega, omega will disappear because remember that I have limits that go from minus infinity to infinity. So you're going to substitute. When you integrate, you're going to substitute for omega to be equal to minus infinity and omega to be equal to infinity at the end. So omega will disappear. What will remain for us is only t. And that's why the inverse Fourier transform will always provide me with a signal that is a function of time. Okay? Right. Now, what is the meaning of this? This is another way of saying the Fourier transform. And if I tell you, for example, this, the integration from minus infinity to infinity of x of t to the power of minus j omega t dt. Yeah? This is the Fourier transform of the signal x. Each time I need to write the Fourier transform of x of t, I have to write it this way? No. Sometimes I'll do something like this. The Fourier transform of x of t. This exactly means the same thing in there. Another way of doing it is they put that scripted f, which is usually okay, symbol like that. Okay, this basically this if I don't know, they call it scripted f. بمعنى if مكتوب بخط معين. Okay, scripted f of x of t again means the same. So if I say that scripted f, or if I write this f of x of t, I mean exactly this. It means the integration from minus infinity to infinity of that x of t multiplied by e to the power of j minus j omega t integrated with respect to t. Okay? So this basically means the Fourier transform. Now, if this means the Fourier transform, then the inverse Fourier transform is nothing but that same function, scripted f, but there's an inverse there. So if you see f inverse, if raised to the power of minus 1 or f minus 1, this doesn't mean 1 over f. It means the inverse Fourier transform. Just like, for example, sine of x. This is the sine of the evaluation of the sine of x. Now sine inverse of x is not equal to 1 over sine of x. Okay, this is not true. Okay, whenever you see sine inverse there or sine minus 1, it is the inverse of sine. Okay, Juan? Meaning the arc sine, meaning the function that is if I put an angle in here in x, I'll get the sine of that angle. If I put the sine of that angle in here, I'll get the angle that corresponds to that x. Okay, and this is exactly the same concept. Okay, so this represents the Fourier transform of x. This represents the inverse Fourier transform, not of x, x of t, but capital X of omega, which will always give me a function of. Now, here's an important point based on what I've just mentioned. Let me erase this. Based on this, what do you think if I do the following? The integration from minus infinity to infinity, okay, of, let's say this is the integration d omega, okay? Inside this, the following: the integration from minus infinity to infinity of x of t multiplied by e to the power of minus j omega t, and then multiply this by e to the power of positive j omega t. What do you think the answer here would be? What did I do? Let me just. This is this thing. This part is the Fourier transform, right? I'm taking the Fourier transform of x of t. I'm taking x of t, multiplying it by e to the power of minus j omega t, and integrating with respect to t. So this is the Fourier transform, that's scripted f, let's say, of x of t, which should be equal to x of omega. And then I'm taking that x of omega itself and putting it in the inverse Fourier transform. I'm taking that x of omega, multiplying it by e to the power of positive j omega t. Let me also add 1 over 2 pi in here. Okay? I'm taking that x of omega, multiplying it by e to the power of j omega t, positive j omega t, integrating with respect to omega, okay? And multiplying by 1 over 2 pi. Anyone can tell me what the answer in here will be, or what? Can we simplify this? Anybody? Gentlemen? Hold on, let me see. Okay.
I think it should be x of t.
Absolutely right. Yes, x of t. Those two operations are inverses of each other. It's exactly the same, since I talked about the sine. It's exactly the same as sine inverse of sine of 30 degrees, for example. Okay? Sine of 30 degrees is 1/2. Take the sine inverse of 1/2, you should get 30 degrees. So this will give you, this will give you 30 degrees. Okay. So if you have two functions that are inverses of each other, if you put one of them, let's say you put a number in one of them, the answer you put it in the other one, you get the original number. This is exactly what I did there. And if I reverse, by the way, it should be exactly the same. If I did the following, if I put the following, the integration from minus infinity to infinity, and then put a box in there, 1 over 2 pi, the integration from minus infinity to infinity of x of omega d, let's say e to the power of positive j omega t d omega, close the parentheses, multiplied by e to the power of minus j omega t dt. Okay? You expect that the outcome from this will be equal to x of omega. Okay? Why? Because this is taking the inverse Fourier transform of capital X of omega, which will be x of t. Like x of t in the outer integration, you get capital X of omega. So those are inverse relationships. One of them takes you from time domain to frequency domain. The other one takes you from frequency domain to time domain. Okay, gentlemen? So this is a very important relationship. Now, I'll talk later, inshallah, about the. Okay, another way. Whenever you have a signal. Don't know, my computer kind of froze. Okay. Yeah. Well, let's say you took. And you found its Fourier transform. Let's say, for example, the Fourier. Let's say this is x of t is equal to sine, and let's say you found x of omega. I'll just throw something. Okay, this is not true, but let's say that x of omega. Or let me even put a number there so that I don't confuse you. Assume that I have a function of time. Okay. A function of time that is equal to sine 2 pi t. This is a function of time. X of t is equal to 2 pi t. So it's a function of time. I took its Fourier transform. So I got x of omega equal to, just for the sake of argument, equal to, for example, cosine omega. And this is not true. This is not the Fourier transform of this. But I just selected two simple numbers. In fact, we'll find the Fourier transform of sine just in a few minutes. But let's say that I found this. We can always write the following: that sine 2 pi t, and you'll see me do something like this: Fourier transform cosine of omega. What is the meaning of this? What is the meaning of this thing that I've written in there? I can say that sine 2 pi t and cosine omega. This is not true. Again, I need to stress this is not true. But if the cosine omega was equal to the Fourier transform of sine 2 pi t, I say that sine 2 pi t and cosine omega are Fourier transform pairs. They are Fourier transform pairs. Meaning, taking one of them, finding the Fourier transform, I'll get the other one. Taking the other one, finding its inverse Fourier transform, I'll find the first one. They almost always, the tradition is to put the time signal on left and the frequency signal on right. Okay? And you'll either see in here ft, or sometimes that's scripted f. Okay? This basically means that if you apply the Fourier transform to sine 2 pi t, you'll get the cosine. If you apply the inverse Fourier transform of cosine omega, you'll get the sine. And this arrow basically indicates that you can go from this side to this side, or this other side to the first side. Okay? So this is basically the meaning of this. Where is it? This. Okay, but okay. Now let's go to, and I'll just mention this now, but we'll talk about it in more detail. If you have a real signal, gentlemen, a real signal, x of t is real, cosine or sine or 3t or 5t minus 7. It's a function that is not imaginary or not complex. When you take its Fourier transform, in general, the Fourier transform will be complex. So Fourier transforms of signals are generally complex numbers, even if x of t is real. Now we'll see there are special situations in which the Fourier transform may be real, but we'll talk about this later. Okay? In fact, we'll talk about it in a few minutes. In fact, it's done. Okay? In here, yeah, we'll talk about it. Okay? I'm saying in here symmetry first of all. If x of t is real, if it happens that x of t is a real function, okay, you'll find that always the Fourier transform of x of t, which is x of omega, yeah, will have the following situation. If you flip it, x of minus omega, it becomes equal to its conjugate. It's what I'm saying here is, if you have x of t, gentlemen, is a real function, okay, the Fourier transform will always be, they call it conjugate symmetric, meaning that if you flip it, okay, you get exactly the same signal, but it's conjugate. Right? Something like the following. For example, if I have, I'm just going to give you an example here on a number, but clearly this is a function of omega. But if you have something that looks like, for example, in fact, I'll give you a function, minus j. I'm trying to think of an example that no example comes to my mind right away. I think something like this. If x of omega, I think, is equal this, Assume that this is the Fourier transform of a signal. Now, if you flip it on the other side, yeah, you get x of, let's say, x of minus omega will be equal to j omega. Now, what's the relationship between j omega and minus j omega? They are complex conjugates of each other. If you notice, those are complex conjugates, meaning that x of minus omega can be obtained by taking x of omega and taking the conjugate of it. Or let me just write it this way, so that I make sure that you understand basically what the meaning of this. Okay, assume that this is x of omega. Let me find x of minus omega. It's going to be equal to j. You take omega and replace it with minus omega. When you remove omega and replace it with minus omega, the minus will cancel with the minus. So I'll end up with j omega. Now let me find x conjugate of omega. Meaning take this thing and take its conjugate. Meaning every imaginary part, change its sign. If you change the sign of each imaginary part, you'll end up with j omega. And if you notice that those are exactly the same. Okay? This is basically what the meaning of this relationship. This happens if x of t is real. If x of t is imaginary, this does not happen. Now, we will never discuss any situation in which x of t is imaginary. Okay? Just real functions is more than enough for you. Okay? So this will always be true. And the consequences of this is that the magnitude of x of minus omega is equal to the magnitude of x conjugate. This is very well known. I mean, if you have two numbers which are complex conjugates of each other, the magnitude or the length of the, let's say the magnitude of them, the square root of the real part square plus the imaginary part square will always be the same. Yeah? Yani the complex conjugate part does not appear in the magnitude. It appears in the phase. It makes the magnitude an even function, and the phase is always an odd function. This is basically what it is. Okay? This basically summarizes to the following. If you know about any function that this is true, it means that the magnitude of the function is an even function. Whatever you have to the right is similar to whatever you have to the left. But the phase is antisymmetric. It's an odd function. If you flip the right-hand side, if you flip it around the y-axis, you need also to flip it around the x-axis to get the same thing. Okay, this is basically what it says about the phase. But some other properties. Okay, this is basically what I was mentioning just a minute ago. If x of t is real, like what I've talked about in here, but at the same time, x of t is an even function, which means it's symmetric. What is this? What does this symmetry or the evenness of x of t, what does it do to the Fourier transform? It makes the Fourier transform purely real. Yani there is no imaginary part in the Fourier transform. You find that the Fourier transform will be just a real function. Whatever, it could be multiple terms added together, but they will be real. And I'll show you examples, inshallah. When I show you the examples, we'll talk about those details, inshallah, later, okay? If it happens that x of t is real, but it is an odd function, x of minus t is equal to minus x of t, okay, similar to the situation here for the phase, then it will happen. What will happen is that x of omega will be purely imaginary. It's not complex, it's just imaginary. You'll find j multiplied by some function of omega. There's no real component to it. Okay? If those are not satisfied, then then x of omega will be it will not be real and it will not be imaginary. It will not be purely real and it will not be purely imaginary, but it will be a mix of two. It will be a complex signal, but it will again satisfy those because it is real. So the realness satisfies those. If it's even, you get an added, let's say, feature, which is that it's purely real. If it's odd, you get an added feature, which is that it's purely imaginary. And I promise you that once we talk about the examples, I'll explain to you this. Okay? Now, does the Fourier transform exist for all functions, all non-periodic functions? And the answer is no. It only exists if the signal x of t is what they call absolutely integrable. Okay? Meaning, if you take the absolute value of the signal, and when you integrate it, you get a value that is less than infinity, then the Fourier transform exists. Okay? This is, I think, an important point. If you take a signal, x of t, and you integrate it from minus infinity to infinity, after you take the absolute value of it, and you find that the integration is less than infinity, it's not infinity, then the Fourier transform exists. Now, this does not necessarily mean, I'll come to your question, Abdurrahman. It does not mean that if a signal, okay, let me say this way. If this is true, I know for 100% that the Fourier transform exists. I can't find the Fourier transform. Now, there are some signals in which, again, if you integrate them from minus infinity to infinity, with the absolute value, you get an infinity. Yet, the Fourier transform exists. Yeah, what I'm trying to say, gentlemen, is that knowing this guarantees to you 100% that the Fourier transform exists. This thing is not satisfied. Does it mean that the Fourier transform exists or not? Or let's say it doesn't exist? No. It basically says that maybe you'll be able to find the Fourier transform. Maybe when you try to find the Fourier transform, you're not going to be able to find it. So this thing, when it's satisfied, it guarantees to you 100% that the Fourier transform exists. If this is not satisfied, maybe and maybe not, the Fourier transform will exist. And I'll show you an example, inshallah, later that will exactly satisfy this situation in which this is still equal to infinity, but the Fourier transform exists for us. Okay? طيب. اتفضل عبد الرحمن, you had, I think, a question.
Yeah, that was, you answered my question.
Okay, good. Thank you. Okay, so this is why I'm saying the above existence condition. Okay, this is the derivation. Sorry, I didn't, because I just added this yesterday. Okay, so I thought that there were some. Okay, yeah. I'm mentioning that. Okay, also, if this exists, if you know, let's say you found the Fourier transform of a signal. This directly comes from what I just mentioned. Okay? If you know the Fourier transform of a signal, okay, does it mean that this is true? No, not necessarily. Okay? Maybe the integration will be finite. Maybe it will not be finite. Okay. And this is kind of the derivation of this. Okay? This basically tells you that why does this guarantee to us that the Fourier transform exists? It's because of this. Don't worry about it. I'll never ask you proofs. Let's say in an exam. Right. The at least last. This is the last, I think. Yeah. This is the last main property of the Fourier transform. There are other properties that we'll talk about later, but those are properties of the Fourier transform that you should understand. It says linearity. If you have x(1) of t, its Fourier transform capital X1 of omega, and x2 of t, its Fourier transform is capital X2 of omega. If I add those two Fourier transform, let's say those two signals in time, and multiply one of them by A and multiply the other one by B, then all I have to do is just find the Fourier transform of x1, find the Fourier transform of x2, okay? Plug this in there, and multiply the Fourier transform of x2 by B, multiply the Fourier transform of x1 by A, add them, I'll get the Fourier transform of the overall signal. Let me call it in here, x of t. Okay? Then what? Let's say capital X of omega becomes equal to the sum of those. Okay? So basically, the Fourier transform is a linear operation. Why is it linear? Because you're multiplying by a signal, a function of time and frequency, and integrating. The integration is linear, and multiplying by a signal, you can always. It's just like multiplying by 3, or multiplying by 5, or multiplying by something. Okay? A system that multiplies by a constant, or without going into detail, a system that multiplies by a constant is a linear system. Okay, it's like an amplifier. Now, maybe to talk about the meaning of negative frequency here. You see, here's well, leave this for the time being. I'll talk about it inshallah later. I promise you, I'll talk about the meaning of negative frequency later. Why are we talking about negative frequency? Because we said that omega, I'm sorry, capital X of omega, if you plot it, capital X of omega, okay? First of all, if I plot X of t, for example, might be something like this. Now we understand what the meaning of X of t evaluated at t equal to 5. And we understand what the meaning of X of t evaluated at t equal to -3. If I consider my present time to be t equal to 0, the current time is t equal to 0. This means that if I evaluate X of t at, let's say, -3, for example, this represents previous time. And if I evaluate the function x at +5, this means 5 hours in the future. We understand the meaning of evaluating a function of time for negative values of t and for positive values of t. This is very well understood. I don't think you have any, misunderstanding in this. But now when we talk about frequency, when we talk about x of omega, if we talk about x of omega, gentlemen, x of omega also has positive frequency and negative frequency. Okay? If you plot x of omega, for example, you might get something like this. Now we understand this is omega. We understand what is the meaning of positive frequency. Okay? What is the meaning of negative frequency? I'll talk about it later, inshallah, because it is kind of a conceptual concept. I'll leave it till later. Okay, so I'll talk about the meaning of negative frequency at later time. But now let's talk about the Fourier transform, or let's try to find the Fourier transform of some important functions. And I'll do, there are tables of Fourier transforms that extend over maybe 5-10 pages. There are Fourier transforms that exist for very complicated functions. And you may ask, why? Who's interested in finding the Fourier transform of very complicated signals? In fact, the Fourier transform, gentlemen, is not something that is only used by electrical engineers. It's something that is used by a lot of fields. Trust me on this, it's used by a lot of fields of engineering. Fourier transform, if you're an electrical engineer, you will use the Fourier transform a lot. The Fourier transform, in fact, is one of the main concepts that you need to understand as an electrical engineer. Other fields, to the best of my knowledge, do not use Fourier transform as much as we do. But there are a lot of situations. You're, I don't know, designing a bridge or designing something in which you need to find the Fourier transform of something. Okay? So the Fourier transform happens in a lot of fields. I remember something. I'll tell you this. When I was in the PhD in the United States, I took a course which was called medical imaging. Medical imaging, basically أجهزة التصوير الطبية. Okay, like I'm sure you know some of those. Like for example, the MRI, the CT scan. There are a lot of the ultrasound. All of those are medical imaging systems. And by the way, I took that course not because I loved medical imaging devices. Okay, it's just that I remember I wanted to take a course. I was missing one course to finish a degree as part of the PhD, not the PhD itself, but I needed to take one more course to finish a specific number of courses so that I can get a second master degree in the United States. So I searched for a course, and one of my colleagues, one of my friends there, told me, "Oh, I'm taking the medical imaging course." Told him, "What is it about?" He told me about this, so I registered it with him, and honestly, it was an interesting and a fun course to take. But I learned that CT scans, the CTs, you know what the CT scan devices do, gentlemen? CT scans take images in a specific way around your body, and they keep rotating. This is why you see, if you have ever been in one of those CT scan devices, it's usually like a ring in which they put you inside. Why is it a ring? Because there is a device that rotates inside of that ring. And it takes images of you while it's rotating. Now, how does it produce those 3D nice images? I don't know if you have seen those 3D images just type, let's say, images of CT scan or of MRI scans. The two devices work completely differently. Okay? But right on the internet, images from CT scans or from MRI, and they'll show you 3D scans of human beings. For example, bones and so on. And they're very nice images. And by the way, I just took a CT scan of, I had a medical issue about 3 or 4 months, and they put me into one of those devices. It took about 10 minutes. And when they put me, this was my first CT scan, okay? When they put me there, I knew how the device worked because I took that medical imaging course. The medical imaging course, or let's say the way that device produces the images, is using the Fourier transform. Trust me, it takes, the device is quite complicated, but it does a lot of, let's say, measurements, and then it takes the measurements and puts them in a Fourier transform to provide you with the image, the final image. So what I'm trying to say, gentlemen, is that the Fourier transform is used by a lot of fields of engineering. Electrical engineering is not, let's say, an exception. It's just one of those fields. Okay. So this is why, because a lot of fields of engineering require Fourier transforms, there were people who sat there and found Fourier transforms for hundreds of signals. And if you just type tables of Fourier transforms, you'll find probably, I don't know, maybe 100, 200 Fourier transform pairs. What we will do here is we'll not talk about all of them. We'll talk only about specific ones of them. Okay? And the idea here is to show you basically what is the process of finding the Fourier transform of a signal. Right? So let's start with one of the fundamental signals that we have talked about. By the way, even sometimes simple signals, if you try to find their Fourier transforms, it becomes quite complicated. But there are some signals that are quite simple to find their Fourier transforms. The first Fourier transform that we will find is delta of t. So let's say if we have x of t equal to delta of t. Okay. Later on, we'll talk about properties, other properties of the Fourier transform. Right? So if we have x of t equal to delta of, I'm sorry, لحظة. Delta of t, yes, delta of t. Let's start with delta of t. Okay, because I think this is one of the easiest. Now, according to this, x of omega, assume that you don't know about those Fourier transform tables and so on. And someone told you what is the Fourier transform of delta of t, which is a very fundamental signal that we have been talking about since the start of the course. Right? You're going to say, well, let me just go and plug in this delta of t in the Fourier transform integration. So according to the Fourier transform integration, it's integration from minus infinity to infinity of x of t multiplied by e to the power of, the Fourier transform has that minus. Remember, the Fourier transform has the minus sign. Minus j omega t dt. If I was finding the inverse Fourier transform, it's without the minus sign. Okay? So this is basically the general formula. So let me plug in x of t, which is equal to delta of t. Integration from minus infinity to infinity of delta of t multiplied by e to the power of minus j omega t dt. Well, okay, I'm stuck in here. I have the product of two signals, right? Anybody can help me here? What can I do here to do the integration? By the way, Muhammad Jari, I noticed that I think you have been raising your hand for a while. My apologies for this. I'll come, inshallah. Once I solve this, I'll come to your question if you have a question. Okay? Anybody can help me here? Fadl, come on.
We put e to the power 0.
Exactly. Remember, I want you to remember this, gentlemen. Okay? Whenever you see an impulse multiplied by any function, we are integrating with respect to t, by the way. Okay? Right? So the x-axis is t. So take the value, the point at which this impulse happens. Where does it happen? It happens at t equal to 0. Remember, the x-axis is t, gentlemen. Okay? The x-axis is t, and this impulse happens at. Why am I insisting on this? Because there are omega, there's omega, and there's t in there. So as if we have two variables, but the variable of integration is t. So determine what value of t will make the impulse there equal to 0. The value of t that will make the impulse equal to 0, or that will make the argument, I mean, of the impulse function equal to 0 is t equal to 0. If t is equal to 0, then the impulse becomes equal to that very high signal. And take now that value of t and plug it wherever you see t in there. Whatever function is multiplied by that, plug in it the value of t equal to 0. So once you plug in the value of t equal to 0 there, I'll end up with, let me write it maybe in another step instead of messing up things. Omega t. So this will be equal to the integration from minus infinity to infinity of delta of t remains as it is. I'm not doing anything to it. I do not plug in t to be equal to 0 there. Okay? So it becomes delta of t, but multiplied by a function that I'm only interested in one point in it. What is that point? E to the power of 0. And e to the power of 0 is simply equal to 1. dt. Okay? And now, you see, this is much simpler than the previous signal. I wouldn't have been able to integrate this because it's the product of two signals. But once I did this, now I can integrate the impulse function, which is going to be equal to 1. And this basically tells me that delta of t forms a Fourier transform pair. They call it this way. This delta of t forms a Fourier transform pair with 1. Meaning, if I have a delta of t which has a delta of t that happens at t equal to 0, its Fourier transform is equal to 1. And I'll talk about this, inshallah, in a few minutes after I answer Muhammad's question. Muhammad, you still have the question?
Yes, Doctor. Is this lecture going to be recorded?
I didn't record. I think I recorded.
Because I'm
I'm recording. It is recorded.
Because I'm heading to the airport and I need to catch on my flight. So may you excuse me
okay.
to...
It is recorded. Yes, it is recorded. It is recorded.
May you
Yes.
excuse me to...
أنا ما باقي لك 15 دقيقة. Only 50. خلاص, it is recorded. Okay?
اوكي.
It is recorded.
دكتور بالله هل بتحضرني؟ لأن عندي
ما أعرف. We'll discuss it later. We'll discuss it later. Okay? We'll discuss it later. طيب؟
يلا شكرا.
Okay. طيب. My apologies, gentlemen, but those private issues, if you want to discuss them with me, discuss them either before the class or after the class. طيب. So we agree now, or what we have discovered is that the Fourier transform of delta of t is equal to 1. Let me explain to you what is the meaning of this, or what is the significance of this. Now we know that delta of t, if you plot it, it's a signal that is equal to 0 everywhere. It's a signal that is equal to 0 everywhere, okay? Except for t equal to 0, it jumps to infinity. And according to this formula, so this is f of t, or this is x of t, I'm sorry, this is x of t, okay? And its Fourier transform, which is capital X of omega, is equal to 1, according to what I've let me just, okay, it's equal to 1. It's equal to 1. طيب. According to what this says is that I need to represent, or let's say if I have an impulse at t equal to 0, that impulse contains all frequencies from omega equal minus infinity all the way to omega equal to infinity. All frequencies are contained in that signal. Now, does it make sense? And the answer is yes, it makes sense. Okay? And I'll prove it to you, by the way. I'll prove it to you, not by mathematics, because mathematics, after all, is mathematics. So I'm sure that sometimes when you see proofs, you think that people are just doing stuff in a way that will make them reach their results. I want to see real proof, and I'll show you a real proof in a few minutes, if you don't mind. Maybe in 5 minutes or so, I'll show you this. Okay? But basically, what this says is that an impulse which takes 0 time, it jumps to infinity, and let's say in 0 time, and then goes back to 0. You require all frequencies from minus infinity to infinity to represent it. Or basically, it contains all frequencies all the way from minus infinity to infinity. Okay? All frequencies are contained in that impulse. In fact, there's a rule that always says this. And I want you to understand it now because I'm sure you'll hear it later in different courses. It says that if you have a signal that is very narrow in time, the frequency content of that signal or the spectrum of that signal is very wide. The narrower the signal in time, look, you cannot have something that is narrower than an impulse. An impulse has basically 0 time. The spectrum of that signal becomes very, very wide, meaning you have all frequencies in that signal. If I replace that impulse with a signal that is a little bit narrower, a little bit wider, something that looks like this, for example. Now, this is not an impulse, but it's something that may simulate an impulse, we said. It's something that is a little bit wider than an impulse. You see that in frequency domain, if this was, let's say, y of t, because y of t is wider than x of t, it has a width that is, for example, 1 second or 1/2 a second or 1/4 of a second, you'll find that in frequency domain, the spectrum will look something like this. Make x of t, or I'm sorry, make y of t even wider, make it wider like that, you'll find that the spectrum of the signal will become narrower. The wider your signal is, the narrower the spectrum of the signal is. So in fact, a signal that takes that increases and decreases very slowly will require low frequencies, or a spectrum is not going to occupy a lot of frequencies. A signal that is very narrow, it requires a lot of frequencies to, it contains a lot of frequencies. Now, how I promise you that I'll show you this, let's say, in a graphical way. I have a program which is called CoolEdit. I don't know if you have ever heard about that program or not. In fact, let me do this. Let me go to Blackboard. Let me stop sharing in here, and I'll share with you my screen. I have a program which is called CoolEdit. It's a very old program, but I have been using it for the past, I'll say, at least 20 years. And in fact, I used old editions of it. And the edition that I have here, I don't remember exactly when I started using it, but it's relatively speaking an old edition. Probably 10. Let me see. Help. About. It's there must be a date in there. I don't see system info. Anyway, I don't see a date in there. Nevertheless, trust me, it's a very old program. And if you want it, I can give it to you. It is anyway. If you like it, I'll be happy to give it to you. I'm using that program for recording audio. It is a very nice program for recording audio, playing with audio. You can cut, or for example, I could record, for example, my speech in here. I can cut different pieces. I can stick them together and so on, and make what I've recorded there sound completely different. So whenever I'm playing with audio signals, I always use this program. It's a very nice program, and it can do a lot of things to programs. I'm sorry, to audio signals. For example, one of the things that it can do to audio signals, although this is not our topic, but one of the things that it can do, it can remove noise. If you have a noisy signal that you recorded, for example, and it's noisy, you can plug it in there, and if you know how to use it, you can filter it, and believe me, you'll see that program do wonders to you. And I always use this program in EE315, at the end of EE315 course, which is probability. I always use this program whenever I have the time to show the students, because this is related sometimes to probability. Noise is basically a random signal. So I'll show them, I'll record my voice, add to it noise intentionally, and then show them that although the signal is very noisy, if you understand how you can, let's say, work with this program, you can remove a significant amount of that noise. But I'm using the program now in a different way. Let me just show you. I'll just record the signal. Sorry. Okay, this is not what I wanted. Okay, control A. Look, this system or this program will allow me to record the signal, and it will show you the. By the way, do you see my screen or not? You see the program, right?
Yes.
Okay, so this will allow me to record the signal just like any other program that allows you to record signals. So I'll just start recording, and then I'll just speak. Okay, and in fact, while I'm speaking here, I'm gonna record. Okay, so now as you see, the program is recording everything that I'm saying. Okay, and it will keep recording. By the way, you can keep it recording for an hour or 2 hours or 3 hours, so it's not gonna stop. Okay, so let me stop it. Now this is basically the speech that I said over the past approximately 10 or 11 seconds. Let me just play it. I don't know if you'll hear the play back or not. Did you hear what was recorded?
No, I didn't.
No.
Anyway, but okay, you didn't hear it because, but I was hearing it in my headphones. Okay. Now the good thing about, or one of the nice things about this program is that it allows you to. This is a signal versus time. The x-axis there is time. If you notice in here, I don't know if you can see where I'm pointing. Let me just make sure that you can see. Okay. Where I'm pointing here at the bottom there, it says hours, minutes, seconds. It's basically the amount of time that it recorded. Okay? So it recorded for about 11 or 12 seconds. In fact, I use this program. If you look at the lecture notes, in the updated lecture note that I'm going to put, you see 2 figures that I got from this program. Okay? That are above in the lecture notes, something like page 30 or so, when I was talking about the impulse response. But anyway, this program now recorded the signal, and it's plotting it for me versus time. It will also show you the spectrum of the signal. Okay? What do I mean by the spectrum of the signal? Meaning it will take this, and at different time instance, it will show you what are the frequency contents of that. If I click on this button in here, it says toggle between spectral and waveform views. And I'll explain to you what this is. This is exactly the same signal that I had before, but this is versus frequency. Now, what do you see here? This is not exactly the spectrum, but this basically shows you that as time progresses from 0 all the way to 11 or 12 seconds, every 1/4 of a second or so, what were the frequency contents of that signal? Meaning, at specific points where I was not speaking, at, for example, around 7 seconds in here, there was nothing. It basically shows you that the signal did not contain anything. It was not recording anything. But at other times, like here, between 7.6 and 7.8, I don't know what exactly I said there, okay? But I said something that contained a lot of frequency contents. In fact, the orange, or let's say the yellow, means the amplitude or the frequency. I don't know if you can see this. The frequency content of that signal between 0 and 1000 hertz. This now, the y-axis in here is in hertz. I don't know if you can see it. And there on top, you have hertz. So it tells you that around 0 to 1000 hertz, I have high amplitude. And basically, the frequency or the spectrum of that signal was very high at that time. Also, between 1000 and 2000, there was also a lot of frequency contents. Between 2000 and 3000, there was some. At higher frequencies, there was a little bit. This is why the color changed from yellow. Yellow is basically very high spectrum. Purple is very low spectrum, and the other colors are somewhere in between. Now, I promise you that this will show me what are the frequency contents. How can I show the frequency contents? What I will do is I'll record now a new signal, and I will clap. And you see that my clap is like an impulse. The frequency content of that clap will be much wider than my speech. Now, clearly, the clap is not an ideal impulse, but it will show you that when you clap, that system or that program will find the frequency contents of that clap at that time, and will show you that the orange in here or the yellow will extend longer than my speech. Okay? To show you that there are a lot of frequency contents. As I mentioned, the reason why it's not going to be yellow or some color that extends from 0 all the way to very high frequency is that the clap, again, is not an ideal impulse. It's something that simulates an impulse. Okay? So what I will do is I'll delete. I will record showing you the spectrum while I clap. So let me record in here, and I'll clap. Okay? Okay. Okay. Notice, when I clapped, what happened? Look at the frequency contents of the clap, which simulates an impulse. Okay. Let me even zoom in just to show you. I don't know if you can. I think I can zoom in here. Okay. Look at the frequency contents. During the clap, I had a lot of frequencies, all the way up to 21 or 22,000 hertz. While during the speech, I think I spoke at the beginning in there. Let me just move there. At the beginning. Look, this is probably speech. Speech contains low frequencies. In fact, by the way, human beings, gentlemen, will only contain frequencies that are between, roughly speaking, 0 frequency, it's not even 0 frequency, about 20, 30 hertz, okay, up to about 2 or maybe about 4 kilohertz. Normal human beings, gentlemen, when they speak, let me even show you this. Here. Record. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and so on. Most of the content of the signal, it's kind of embarrassed me. I don't know why there turned out to be some high frequencies in here. But most of the contents, if you notice, are about 4,000 hertz. What do you think will happen if a woman was speaking in here? Anybody can guess what will happen? Now, it's not soft, but it's not very kind of. There are people who speak like this. Hello. Okay. What do you think will happen if I bring a woman and she speaks in front of the microphone here? Anybody can guess?
you will see a higher frequency spectrum.
Yes, yes, okay. And I'll try to simulate it. Please do not laugh. Yeah. I'll try to simulate it. Hello, how are you? Okay. Sorry for that. Okay, but now you notice that the frequencies now are a little bit higher, I think, in my opinion. I don't know. It looks like it's, in fact, let me do both things, and I'll stop. I promise you, after this point, I'll stop. Okay? Hello, how are you doing? Hello, how are you doing? Sorry for that. Okay, but you notice the difference between the two. Okay? The left one was for maybe a man. The right hand side, or the right one, was for a softer voice, which contained higher frequencies. That's in fact why the human being can hear the voice, and you can generally tell whether it's a man's voice or a woman's voice because of the higher frequencies. Okay, so I'll stop at this point. So next class, inshallah, we'll talk about also the Fourier transform of some other functions, and we'll talk about some of the properties of the Fourier transform. Anyway, we'll continue from this point. My apologies, I'm not going to be able to give you a problem session during the class also tomorrow. I know that a lot of students sometimes love to have the problem session on the day of the exam or so. It's just that we are a little bit behind, and I need to speed up. Okay, if I give you a problem session here, I doubt that we'll be able to complete the course content. Okay, Juan? But anyway, I'll be available and if you have any questions or comments until maybe, as I mentioned, 3. If at 3 there are some questions, I'll continue until 4. If at 3 I find that no one has any questions or so, I'll probably stop. Okay, Juan? Yeah, whatever time after 2 I find that there are no additional questions, I'll stop. What I will do, gentlemen, is I will enter into the Teams group that I set for the course, and I'll be available there. So if you have anything, just go there. You'll find there is a session that is open. Just log into that session or connect to that session and ask whatever you have. Okay, Juan? Okay. So I think maybe one of you has raised his hand, I think.
If we send you a question by email, will you respond today? Or maybe tonight?
Inshallah, I'll try. But I don't promise you that I'll be able to respond in time, let's say. I'll try my best, honestly. Okay? I'll do my best to respond to questions. And I prefer that you do it this way. I prefer email. Email is kind of inconvenient. Do it using Teams, okay? In Teams, if you just send anything through the chat to me, I'll try to go over Teams later today. The problem is, I prefer that you don't send it through WhatsApp. And the reason why, if you send it through WhatsApp, it will probably get lost, is that I have probably 200, 300 messages, probably even more, that I haven't read, that are scattered here and there in WhatsApp. And if you send it, I'm afraid that it will get lost. If you do it using Teams, probably I'll be able to respond to it, okay? But I'll try my best, I promise you. I'll do my best to respond to all of your questions as much as possible. Even if you send it at night or so, I'll try my best. But the lecture is over. If you don't have any questions, I'll see you tomorrow. If you have any questions, you can either talk to me right now, or you can ask me later, maybe in an hour or so.
Doctor?
Further.
Will you join team now?
Yes, I'll do it right now. Just give me maybe 2 minutes, 3 minutes. Let me just close Blackboard and I'll join the team. Okay?
Okay, fine. Yes.